This is the first of a two-part video on stoichiometry of gas mixtures. In the last video, we talked about the ideal gas law, and in this video, we're going to use some non-traditional uses of the ideal gas law with some new variables. So the focus points will be on calculating density and molar mass in this video, and in the next video, partial pressures and stoichiometry. So what we talked about in the previous video were macroscopic physical properties of gases like pressure, volume, temperature, and number of moles. And these are properties that are state properties. They're the same no matter what the gas is, but there are other variables that do vary depending on what the gas is. And so we'll call those identifying variables. These are variables we'll want to solve for to figure out what is that gas in the balloon. So the two variables we're going to practice with are density, which we all remember from intro chemistry is measured in grams per liter, mass over volume, and the other one is the molar mass. That's measured in grams per mole. So these are variables that will tell us what the composition of the gas is. So now our question is, how can we use the ideal gas law to learn the identity of the gas? So let's try molar mass first as an example. So molar mass, the unit is grams per mole. So that means it's going to be the mass, m, over that number of moles, which is n. In my opinion, they must have chosen n to represent number of moles because m was already taken, so they just picked the next letter. So we've got the molar mass formula and the ideal gas law. And we're looking to somehow use this formula to find molar mass. And so we can see number of moles is here in both of them, but we don't have m. There is no mass in PivNerd. So we have to find a way to insert m into this formula to use it. So I am going to rearrange the formula to isolate the part that I know that I need. So I'm going to isolate 1 over n. And I can do that by moving it around. So that gives me RT over PV on this side. And then what I want to do is I want this side to say m over n. So the way math works is that you can do whatever you want to an equation as long as you do it to both sides. So if I want this to say m over n, I'm going to multiply this side by m. And so then I have to multiply the other side by m as well, so that it's equal. So now m over n, that is molar mass, the variable that I wanted. So now I'm going to substitute molar mass. So now molar mass equals RT times M over PV. So this is how we managed to insert the mass and insert the molar mass into that formula. So now, if we were to plug in some of these normal variables, these macroscopic properties, we can find the identity of this gas. We can do the same thing for density. There's density formula, mass over volume. Here's PV equals nRT. We know the volume and it's in both the formulas, but we need to insert the mass into the ideal gas law. So we'll do the same thing. We'll isolate the part that we have. So we'll rearrange to get 1 over V equals nRT over P. And then we want this side to say mass over volume. So we're going to multiply by mass on both sides. And then we're going to substitute m over v for density. So substitute for density, and we end up with density equals oof, guys, this is upside down. Hang on. Let's make a change here. This needs to be 1 over v. So this fraction is upside down. So this needs to be p over nRT. And then we'll multiply that by mass. And now we should have density equals m times p over nRT. That was a close one. So this is one way that you can do it. You can substitute in the variables you need into the ideal gas law. If you like, in many cases, you can also just solve the ideal gas law for whatever variable you don't have, and then plug that into the next formula and just do it in 2 steps. So either of these is a functional way to do it. I would highly recommend not trying to memorize these new formulas we've just invented, because they're easy enough to find on your own. Don't fill your precious brain space with things that you don't need. So let's do an example of a problem where you might need to find the identity of a gas. So here's an example problem, and it says we have 1.27 grams of nitrogen oxide, but we don't know which nitrogen oxide. It could be NO, or it could be N2O in the balloon. So we have to figure out what the identity it is. So it has a volume given, and its temperature, and its pressure, and it wants to know which oxide it is. So which oxide wants to know about identity? And if it wants to know the identity, we need to find density or molar mass. And in this case, I don't know the density of nitrogen oxides off the top of my head, but I could definitely find the molar mass using the periodic table. So I'm going to choose that one as my strategy. So molar mass is mass over number of moles, ideal gas law, PV equals nRT. Whatever combination of these two, one formula or 2 formulas, your choice. I'm going to do it in 1 step here, since we already found the formula on the last page. All right, so we just need to plug in all of our variables. So we've got the temperature was 25 and convert to Kelvin. We have the mass, 1.27 grams. We have the R constant. I always put it last for some reason. I think it's just because it takes up so much space. Okay, big fraction bar, and then on the bottom, we have the volume, 1.07 liters, and the pressure, 737 millimeters of mercury. And then we want to double check that our units are the same here, because I used Kelvin, I used liters, the grams and the moles will become the unit for molar mass, but I have atmospheres here and millimeters of mercury here. So one of them needs to be changed. You can change either of them, it doesn't matter. So I'm going to change the bottom one to atmosphere because I have more space left down here. So 760 millimeters of mercury goes to 1 atmosphere. There's our big fraction. You can plug that into your calculator and find 29.9 grams per mole is our molar mass. All right, so what does this tell me? Nothing yet. It doesn't tell me anything yet because I don't know what 29.9 means. The question asked for the identity. So what I need to do is I need to find the molar mass of each piece and compare to the molar mass of my unknown so I can do a match. So nitrogen oxide is going to be 1 nitrogen and 1 oxygen. So here's our periodic table. This one does have numbers on it, though they're quite small. So nitrogen is 14.007 and oxygen is 15.999. Any periodic table should say the same. So we're going to do 14.007 grams per mole for nitrogen plus 16 plus 15.999 grams per mole for oxygen. And then for nitrogen dioxide, we are going to add a second oxygen. So 2 times, oh, no, it's 2 times nitrogen. 2 times nitrogen plus oxygen. It wouldn't really be science unless it had mistakes in it, right? We all know how to make mistakes. Okay, and so this one at the top should be right around 30 grams per mole. I'm ballparking it here. And this one should be 42 grams per mole. So if we compare that to the one we had in our problem, the 29.9 is much closer to the NO than the N2O. So that means the oxide in question is nitrogen oxide, because that one is the lighter of the 2 oxides. So this is an example of a non-traditional use of the ideal gas law. They can give you really important information about the identity of your gas. In the next video, we'll talk about how to do stoichiometry and partial pressures when you have more than one gas together in the container.